Good afternoon. Welcome to our third session for our Galactic Centre Star Party live stream weekend. As usual, before we begin, I would like to say that in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respects to the elders past and present and extend that respect to all Aboriginal and Torres Strait Islander people today. So this afternoon, we've got our third stream, the solar session with ASV Solar Section Director Russell Cockman. Russell's going to share his knowledge of the sun with you. So without further ado, and with all of the clouds that we've got, let's have a chat to Russell and a look at the sun, if we can. Good afternoon, Russell.
Well, thank you very much, and good afternoon to you, Mark, and good afternoon to everyone who's joining in. So, yep, we've got a few clouds here in Melbourne, but we have a plan B available.
We do have a plan B.
And you should always have a plan B. It's very important. So I just want to speak to you just for a few minutes by way of introduction to tell you a little bit about safe solar observing, because in principle, it is a pretty dangerous thing to do. So here's the warning. Now, when you look up into the nighttime sky, you see thousands upon thousands of stars. And it's quite safe to look at those stars with your eyes, binoculars, or a telescope. But our sun is very, very different because it is so close. The sun is hot, gives out a lot of light. So please do never look at the sun directly with a telescope, binoculars, or even your eyes. And why should you not do that? Because there is a risk of permanent injury to your eyes. So please, no one wants to have their eyes damaged permanently. So please do not look at the sun through telescope, binoculars, or even your eyes, unless, and there is always a proviso here, unless your equipment has proper filtration that reduces the amount of sun's light and especially the heat that will exit the eyepiece and potentially cause that damage. So please, there are safe ways of doing solar observing, but please make sure you have proper solar filtration to reduce the sun's light and especially the heat before looking at the sun. Now, there are a couple, three actually, safe ways of doing it. And the first way is using white light filtration. So here we have a telescope with a metallized film of plastic over the front, which is known as a safe solar filter. And a company called Barda make these solar filters. And so effectively, all, 99.999% of the sun's light and heat are removed from the stream before it even enters your telescope. And this is a very, very safe way to observe the sun. But please, I will advise you, warn you that before you put that filter on your telescope and before you even attempt to use your telescope to look at the sun, hold the filter up to the sun and move the sun around and make sure there are no pinholes or any scratches or damage in your filter before you actually put it onto your telescope, be it a refracting telescope using lenses or a reflecting telescope which uses mirrors. Always check to make sure that the filter is in perfect condition before putting it onto your optic and before looking through your optic at the sun. And this is what, on a very good day, this is what you would hope to see on the sun. A beautiful ball, which is the actual sun, and you'll see these black spots on there, which we call sunspots. And looking at that image of the sun, please bear in mind that the sun is big. We can put 109 Earths across that sun. So when you, with your imagination, you put 109 Earths across that sun, just imagine how big those sunspots are. They look quite small, seen on the sun itself, but the sunspots are huge compared with this little speck of dust, moist dust that we call our Earth. So these are huge. And we have a number of beautiful sunspot groups on the sun as we speak today. So hopefully after this talk, which we will be able to have a look at those in real time. Fantastic. So that's called white light filtration. You'll see sunspots. You might see a little bit some whiter areas around the edge, which are called faculae, but you will not see the prominences coming around the edge of the sun. What you need is a slightly more refined filter than that. I should have mentioned price. These solar filters that we see here, you can buy them ready-made for your optic, or you can make them yourself. But if you want to buy one, we're looking at perhaps $100, maybe $200, just depending on the size of the filter that you wish to purchase. Just $100 or a couple of $100. And then there's the hydrogen alpha way of looking at the sun, and this is the Astronomical Society of Victoria's hydrogen alpha solar telescope. Just looks like a refracting telescope, but down here where this little controller is, there's a very, very special optical device here, which only allows a specific band of wavelengths through. And for hydrogen alpha, that wavelength is about 656 nanometers, which is deep into the red area of light that we can see. And for this presentation, you can put an eyepiece on the end, or here there's a video camera. But one thing I really want to point out to you is that a hydrogen alpha solar telescope actually consists of two filters. There's the one filter here that selects the hydrogen alpha wavelength, and just a tiny band either side of it. And invisible in this telescope is in this area here, the draw tube we call it, is an IR block. Now IR is infrared, and that stands for heat. So the invisible in this telescope is another filter that removes the heat from getting to your eyes or to your video camera. Extremely important. And these hydrogen alpha telescopes will cost up to, depending on size, several $1,000s. This one you see here is was purchased for about $10,000 a few years ago. So a lot of extra money involved, but well, what you see is outstanding. You'll now see a red sun, because that is the color of hydrogen alpha light that we see with our eyes. You'll see some sunspots. Here we are. You'll see some active regions, these brighter white areas here. That's where explosions equivalent to perhaps millions of atom bombs going off simultaneously. The amount of energy produced in these active regions, blasting stuff into space. You'll see prominences around the edge. Have a look at the number of prominences around the edge of the sun, and you'll see these with your own eyes, looking through a hydrogen alpha solar telescope. Look at this beauty here. Fantastic. Once again, 109 Earths will fit across this image of the sun. So just compare the size of this prominence compared to the size of the Earth. I reckon we could probably fit half a dozen Earths into that prominence there. Prodigious. Absolutely fantastic. Also, you'll see some filaments, and hopefully we'll see some filaments today. And here's a filament right here. These are actually prominences seen silhouetted against the surface of the sun. Now, what we see here are all shades of red, okay? And bright red indicates regions which are slightly hotter, perhaps a few hundred degrees hotter than the average temperature in the vicinity. And filaments, because they appear a little bit darker, are a few hundred degrees cooler than the average areas around them. So really what we see on the sun, it's all to do with subtle differences in temperature, just a few hundred degrees Celsius. So the average temperature we are seeing here on the sun is about 5,500 degrees Celsius. This region here is a few hundred degrees hotter than that. These filaments are a few hundred degrees cooler than that on average. So it's all to do with subtle differences in temperature. And I think we will leave that today, but I will just finish up with what is solar activity. Well, solar activity can be measured by the number of sunspots we see on the sun. This view that you can see here, lots of sunspots, mean the sun is quite active. And we're not looking at the fact of heat and light, but we are really looking at the sun's magnetic activity. Other times when we look at the sun, we don't see any sunspots at all. And this is a time when we'll say the sun has low activity. It still gives out the same amount of heat and light, but it's magnetically less active than it is at other times. So by talking about solar activity, we are talking about the hidden magnetic activity of the sun. So I reckon we should leave these pictures of the sun and go and have a look at some real-time images and views of the sun. So let's go. I'll stop sharing and over to you, Mark.
Oh, I'm going to bring Lee in. So
Lee?
Russ, Russ, while you're, I don't think we're going to be able to get a live view just yet. We do have Anne-Marie hoping to get some clear sky. Lee's got nothing but cloud at the moment.
Okay.
Yeah, the sun's here somewhere.
So
Maybe.
I'm wondering, Russell, for the time being, while we wait to see if Anne-Marie can get some clear sky, if you're able to share with us some of your the sun footage that you recorded the other day.
Absolutely, I would love to do that, Mark. And so this is actually a plan C.
It is a plan C. It's a plan C.
Yes.
Anne-Marie still doesn't quite have clear skies.
Okay.
We'll have plan D, E, and F if we need to.
Well, I will very much like to do this. And so here we are. I always have trouble with this. I have the screen. I have a share. Okay, so I shall.
I'll remove
share
Lee's from
screen.
it. And just so you know, Russell, Dave says that the sun is shining in Beveridge.
Right. Well,
there's a beverage near me.
We need that down here, Dave.
Window, right. And here we go. I'll share these. Right, so can you the videos?
Yes, there we go. Beautiful.
Now, if I click on a video, will it open up in a video stream? Will you see it?
Well, we'll soon find out, won't we? If it doesn't, then you just
sharing. I think that's sharing that.
Yeah, I think you're just sharing the folder. You might actually have to share the other screen.
Yeah, so stop sharing once you've opened that up, Russell, with VLC. You'll have to share VLC.
I'll open up a video folder in a file in VLC. Okay. And then now I shall go to share screen.
We will get there.
Yeah, absolutely. And a window. Here we go. Hopefully you can see a sun now.
Yes. Now we're talking. So when was this
ladies
one
and gentlemen, this was recorded on the 8th of September, just 3 days ago, from sunny Elwood. And this is through the Astronomical Society of Victoria's Hydrogen Alpha Telescope that you saw a few minutes ago, but using a monochrome camera, i.e. it can only register lots of shades of grey. But hopefully you'll see as this video plays. Here we go, playing this video. You can see exactly what hopefully you would expect to see, some active regions. Here's an active region here around several sunspots, and these sunspots have been given a number. And this is the active region 2866. Here's another active region, 2868. An active region up here, which is 2864, and an active region down here, which is 2863. Like all good scientists, we like to put numbers to these things so that in the future we can refer back to the sun as we saw it on the 8th of September and wax lyrical about these wonderful active regions that we saw. So hopefully you're getting good views here. Now, if you look very, very carefully, you can see the surface of the sun here. And really, bearing in mind the sun is just a big ball of gas, so it's not actually a solid object we're looking at, but we're looking at a surface of the sun called the chromosphere, a very different surface to that sun we see in daytime, the blindingly bright surface of the sun, which is called the photosphere. So it's a very, very neat thing that, depending on what kind of telescope you're using to observe the sun safely, you're looking at different layers of the sun, a bit like peeling away layers on an onion, for example. And so this beautiful red chromosphere that we're looking at, but we're only seeing it in shades of gray, is about 10,000 kilometers above that brilliant white photosphere that dazzles us during the daytime. Slightly cooler layer above that photosphere. Wow. And all this little light and shade you can see around here, that is all real structure on the sun's chromosphere, as are these active regions here. And oh, there's a filament here and another filament there. And if you look very, very carefully, you can see the sun is sort of wobbling about a little bit. That's not because the sun is boiling. That is simply because we're viewing through the Earth's atmosphere. On a relatively hot day, the Earth's atmosphere acts all these heat convection currents rising up. That they act like little lenses which subtly change the position of these features. Okie dokie. So here we have a beautiful sun. Once again, imagine 109 Earths will fit across that. And I'll have to say, just a little bit conspiratorially, doing a live stream of the sun is undoubtedly the safest way of viewing the sun, because you're not actually viewing the sun directly. You are viewing it indirectly, and it's a perfectly a safe way to observe the sun.
So we have a question for you, Russell. Just because you were talking about the surface, you're talking about all the different elements on the surface there. So Shannon wants to know if you could stand the heat. So just say you didn't burn up, would it be possible to walk on the surface of the sun?
Well, I guess you could, but you've already given that proviso if you don't burn up. Well, yep. The sun is a hot place, and bearing in mind it's not a solid object, and it has an intense gravity field because of its huge mass. So there's really nothing solid to walk on. So effectively, you just fall all the way to the sun's core, because there's nothing solid there to counteract the force of the sun's gravity dragging you in. So with all those provisos, probably not. You couldn't.
Probably not. So even if you don't burn up, you're still not going to be able to walk on the sun.
Not a solid object.
Yep. There we go. I'll let you continue on now, Russell.
Okay, well, I'll stop sharing this and go to another video, because I've got lots of them.
That's good.
So as I said, that is the full sun, and that's a beautiful view through the ASV's Hydrogen Alpha Solar Telescope, full views of the sun. But notice, we don't see any prominence. Oops, I've stopped sharing, so I can stop talking about that. Let's go to another video. Here's another one.
We're waiting for it.
Play that. Let's go and share it.
Technology, can't live with it. Can't live without
Brilliant.
it.
So here's a close-up, ladies and gentlemen.
There we go.
Of those two active regions. I hope you're enjoying this. Isn't this fantastic? Please reassure me, Mark, that you can see it.
Oh, yeah, yes. We can see it. Yeah.
Fantastic. So these are the active regions 2866, which is here. It's not just one sunspot, but at least 4 sunspots, and here are 3 sunspots close together. And there's because we've got whiter areas here, there's a slightly hotter, a few hundred degrees hotter. So these are active regions where smallish explosions as far as the sun is concerned, but explosions releasing millions upon millions of times the energy of an atom bomb simultaneously on the sun. And active region 2868 over here, Now, although these sunspots look dark, if we could isolate a sunspot and look at it, it would be as bright as the sun. So the reason these things look dark is simply a matter of contrast. They are still very hot and very brilliant. But I want you to notice the wonderful structures around these sunspots. These are structured because of the sun's magnetic field, just moving around on the surface of the chromosphere here and causing the sun's plasma to follow those magnetic lines of force. How fantastic is that? And just wanted to point out as well that our Earth could fit quite comfortably within this sunspot just here that I'm highlighting. The Earth would fit quite comfortably into that. And here you can see the heat haze from the Earth's atmosphere causing the edge of the sun to ripple a little bit. That is not the sun doing that. That is the Earth's atmosphere creating that illusion. And gee, if we look very, very carefully on the edge here, there's a little prominence just there. When I say little, that is all relative. It is little compared to the immense size of the sun. I should put a number to this. The sun's diameter is 1.4 million kilometers. 1.4 million kilometers in diameter. Wow, how fantastic is that? And once again, all this stuff here, that is all structure on the sun's chromosphere. Some little white spots there are sites of relatively small explosions. In this region here, there are some slightly whiter spots. And I will perhaps I'll finish this video and go to a little bit later in time, and you'll see the timestamp come up when the video restarts. Thanks for mentioning me in a comment there, Lee. Thank you. This was taken at almost 17 minutes past 2 p.m. on the 8th of September. So I will finish this video and I'll stop sharing it, and we'll have a look a little bit later on, because this is the marvels of having pre-recorded videos.
We can jump around to where we want. While you find your next one, I'll just pop this image up with, that Lee has taken. So we've got something to have a look at.
Okay. Fantastic.
So Lee's just going to zoom in on that. Let us know when you're ready. We're ready with the next one.
Are you talking to me, Mark, or?
Yeah, let us know when you're ready with the next video.
I haven't got any more.
I've got plenty of them.
Right. Keep them coming, and
okay.
For the viewers, keep the questions coming as well, because Russ will answer them.
Oh, I love questions.
The more questions we have, the better.
I'll share screen.
While you're doing that, I just want to let everyone know that we are now under less than 200 raffle tickets left out of the 1,064 that we had for the Ioptron Skyguider. So thank you to everyone who has bought a raffle ticket. And to those who haven't, you still have a chance. The link's on our Facebook page and on our website. So grab them before they go. We have a question for you, Russ, from Tony.
Fantastic.
Tony wants to know, what drives the color difference between Lee's image and Russ's pictures?
Well, I didn't see Lee's image, but
it's yellow.
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 Okay. So that would be due to the kind of filter that is used. I'm presuming that Lee's filter that he uses allows yellow light through. So is that right, Lee?
No, not quite. It's more a bit of wizardry and fakery. I've only got I've got the white light filter that you were sort of mentioning earlier, which is the pretty standard sort of solar film type thing. And I'm fairly sure I took it with a mono camera. And with our wonderful Anne Marie gave me some hints on some processing where effectively I've done the stacking of the images, a whole lot of images, and then processed them in Photoshop, which brought out a lot of this, the beautiful sort of the stippling, you get everywhere. And then really just grabbing a color palette and saying,
Right.
"Does that look right?" and
Yeah.
adding it. So it is fake, but
No, you've added the color in post-processing, we would say.
correct. Yeah.
And really, you've chosen a yellow color because the sun is actually a yellow star. So you're trying to make the sun look a natural color, all right? Which
pretty
reflects
much.
all of the colors of the sun, all the colors of the rainbow that the sun sends to us, all mixed together. So really, that answers the question that you have added a yellow color just to make the sun appear a natural color. But there are a number of different kinds of filters out there, and as I say, the hydrogen alpha allows a little bit of red light through, so we see red suns. And there's another kind of filter called calcium K, which makes the sun look a deep blue color, which is truly indicative of the wavelengths of light that the filter allows to pass through. So that's why when you go to a NASA site like SDO, the Solar Dynamics Observatory, you'll see some images there of all ranges of colors. And those colors have been chosen, if they're visible colors, to represent the wavelengths of light that the filter allows through, or if they're wavelengths of light that our eyes can't see, then colors are added later just to give a visual cue as to the kind of wavelengths that are being used. So it's all down to the filtering and often a little bit of post-processing there.
So just
Excellent
quickly,
question.
Russ.
Thanks very much for that.
Just quickly, the raffle, being asked when the raffle's drawn, that's going to be drawn around about 9 o'clock tonight during our Space Invaders themed Deep Sky session.
Fantastic.
So you've got a little bit of time still to grab some raffle tickets. Now, a question for you, Russell. Astronomical Society of Geelong would like to know what camera are you using for the video shots?
Well, I'm sorry about that. I was trying to think of competition and etc. But no, it's wonderful to have you join in the Astronomical Society of Geelong and keep up the good work down there, guys. Pity. So this camera is a ZWO ASI 174mm. So it's a fairly large chip on it, which means that the whole disk of the sun can be viewed at once, and it's got technically it's got quite a deep well depth, so it's got a good dynamic range available, and I'm really enjoying the dynamic range that this camera is providing. It's really an excellent camera, and I'm delighted I purchased it for showing off the sun. So I hope that, so it's a ZWO ASI 174mm video camera.
So we have some more questions coming through for you, Russ. Brenton Rashid, this is a two-pronged question. This one's one for Lee, and one part for Lee and one part for Russell. So Lee, Brenton wants to know what software you use to image.
Yes, so with my ones, it was it was either SharpCap or Fire Capture, right. And effectively taking a video for probably 10 minutes or so, and then well, probably even less than that now that I think about it, being the sun, it would have been sort of higher frame rate. That video is taken in a format with a, I don't actually know the what it stands for, actually. The .ser files, they're like an AVI file, but they contain some extra information, and they're significantly large when they're made. So it would have been maybe a 20 or 30, probably even more, gigabyte file, and subsequently grabbing that video file and putting it into AutoStack it, sorry, which grabs all the best images out of that, and which is, in fact, if you just quickly go back to my screen, maybe Mark.
Okay.
Which here we can see there's what is it? There's around about 96 different images here. So it effectively grabs every one of those images, and it if I just scroll through these, it looks like a video, but they're effectively the best images within that 5 minutes of video, and then it stacks them all together as a single file, which would have been probably one of these here, which is a 90 megabyte TIFF file. Then just grab it into Photoshop and go through the extra processing to fix the image up a little bit more and give it the color.
And then the second part of that question, Russell, is for you. Why is it that the corona of the sun is hotter than the chromosphere?
Well, that is the $64 billion question, because that's about how much scientists have spent on getting solar probes up into space and observing the sun. And the Parker solar probe, okay, it's not $64 billion, but
close enough.
But close enough, yes. So please, Brenton, that's an excellent question, and it remains to be answered. But the Parker solar probe, its prime mission is to plunge deep within the sun's corona and measure the magnetics and all the other things that it can measure to provide information about explaining why the corona is so much hotter. And perhaps I should add a few numbers that the surface, the photosphere of the sun is about 6,000 degrees Celsius, whereas the corona is 1 or 2 million degrees. The corona being the sun's atmosphere. And of course, we know that heat travels from hot to cold. So and because the corona is further away from the sun than the photosphere is, why is the corona so much hotter? But I think we will discover that it's because of magnetic effects within the plasma of the corona that provides heating of the corona.
Could
Excellent question.
Could it possibly, Russ, have any similarity to the fact that when you boil a kettle, the steam is actually hotter than the boiling water when measured?
As a scientist, you would find if you put a thermometer in boiling water, you would find that the temperature of the water would be 100 degrees C, and if you put a thermometer in the steam, it would be 100 degrees C as well. That's just it's just the way it is. If it's at atmospheric pressure and it's an open system, then the steam would be the same temperature as the boiling water. In a perfect world, okay, there are various effects that would come into play that might reduce the observations somewhat, but in a perfect world, the temperature of the boiling water would be the same as the temperature of the steam above it.
Now,
Okay.
Russ, have you got some more?
Yes.
While you're doing that, a question for Lee to answer from Brenton again. Hard drives, what sort of capacity do you have, considering these files are so large? And I know you also do astrophotography, so you do a lot of imaging, whether it's the sun or planets or deep sky stuff.
Yeah, look, the thing is, working in media as well, I've got tens of terabytes of hard drive space. It's never really an issue as far as storage goes. Again, maybe if you just quickly flick back to my screen, then what I've got is my imaging. I don't know if you can see it. Can we see it in this one? We can there. So when I'm doing any imaging, there's the mount and the telescope, but I've got a mini PC here that's just got a 256 gig SSD drive in it, so that's nice and fast. But you'll see a network cable here. That's at the moment that's running back into the garage where I've got servers and various other things. So what I do is I mount a hard drive, a drive here, back to my network. So what I do is I've got anywhere I do any sharp cap stuff. So we can see this is a couple of weeks worth of imaging for stuff I've done, deep sky. There's Nina as well. when I use that. So tarantula I did the other day. And there would have
Focus
also
on the sun,
been...
Lee. Focus on the sun.
Yeah, I'm trying to... Oh, see, I haven't got them there, but what I had done was it would be... No, it's not there. So what happens is this is kind of a temporary storage area. And then once I've got all my images there, I move them over to my PC, which I can't sort of show the share from here, but that's where I've got a lot more space. And definitely tend to work with SSD for sure, because it's just significantly faster and can handle and these. In fact, those drives that goes to is SSD, but it's just a partition on a virtual machine, so I can make it as big as I want.
There we go. Hopefully, it answers your question, Brent. Now we're going
to. And for Brenton's information, I use fire capture for capturing these videos.
Got your sun back again, Russ.
Fantastic. So I've just upped the contrast on this image just to make the light and shade a little bit more prominent, shall I say, easy to see. And look at the wonderful structures around these sunspots. As I said, that is simply plasma following the magnetic lines of force around them. And I just want you to notice that in general, the white areas have about the same level of whiteness. Okay, over here we got a little bit brighter, but I just want you to focus on this area just here and a little sort of a whitish area here, because next video I'm going to show you a flare, i.e. an explosion taking place on the sun. A relatively minor flare, but nevertheless millions of atom bombs going off simultaneously. So the timestamp coming up right now is 18:47 minutes after 2 o'clock. So I'll just shut this video down and show you another one. I hope you're all still with me.
Oh, they are. Yeah. We're all watching. People are still watching.
So I think over to this one here. So that was about 10 minutes later, ladies and gentlemen.
So you got another one coming now?
Yep, coming up. I shall share it.
There you go. Hi, Russ. Still with you. See?
Fantastic. Thank you very much. Reassuring. But there we go.
There we go.
So this is the same area and pretty much the same exposure conditions, but look how bright this area is now. So that brightness is an indication of an explosion taking place around that sunspot group. Magnetic lines of force just coming together and recombining and releasing all that stored magnetic energy and creating a hotspot on that active region. And as I said, releasing millions of atom bombs of energy almost instantaneously.
Amazing.
How good is that?
It is. It's brilliant. You'd sit and watch it all day, couldn't you?
We could.
But
yes.
not at night.
No.
There
are all those other suns to enjoy night.
There are, aren't there?
And people, ladies and gentlemen listening, and girls and boys listening in, these flares may only last 10 or 15 minutes. Okay, so they are very transient events, and it just is a matter of luck that I happened to be videoing the sun at this particular time. Now, please bear in mind, this is a relatively low intensity flare. The intensities of flares are ranked on an alphabetical scale, and this one going in powers of 10. So this one is a C-class flare, and then above it is an M-class flare, which are typically 10 times more powerful than C-class flares. And then above that you have the X-class flares, which are 10 times or more powerful than M-class flares. So an X-class flare would be about 100, 500, maybe even 1,000 times more energetic than this C-class flare you're looking at the moment. So the amount of energy involved is prodigious.
Now, Russell, we have a question regarding these flares from Anthony. Is there any
Hi,
way
Anthony.
to predict their location, or is it completely random?
Well, a good question. Thank you very much for asking that. But in general, flares arise from sunspot regions. Sunspots are a visible sign that there is magnetic energy, powerful magnetic lines of force coming out of the sun's surface. And it's when these magnetic lines of force connect together that energy is released in a flare. So flares in general occur around sunspot regions, active regions which contain sunspots. So from the point of view is, yes, we can predict where flares are most likely to come from, but we can't easily predict when a flare will occur. I mentioned these solar probes up there, SOHO and SDO. They can actually measure the magnetic polarities of these sunspot regions. And based on the measurements of these polarities, they can actually measure how much magnetic energy is stored there, and therefore be able to predict that when that magnetic energy is released, what the intensity of the flares might be. And there's a wonderful site called spaceweather.com, which up on the top left-hand corner shows an image of the sun and sunspots on it. And they will actually say in a little description underneath that sunspot region 2868 harbors energy for M-class flares or X-class flares. So therefore, yeah, we can't actually say when a flare might happen, but the information available can at least predict what intensity of flare might be when it erupts. And the X-class flares, they're exciting because they can, if they're Earth-directed, they can blast billions of tons of sun stuff earthwards, which can lead to displays of the aurora australis for us here in the southern hemisphere, or the aurora borealis in the northern hemisphere. So it's exciting times. Okay, so I will stop sharing that. And let's have a look at some prominences now.
I was just about to ask you, have we got any prominences
Yeah.
we can look at? I know Lee's downloading some images that Anne-Marie took
Fantastic.
of the solar prominence, of some prominences. So
I shall now share a prominence video.
there it comes.
So here we have it. So this is a loop prominence, and you can see the sun here is overexposed. That's because these prominences at the moment are relatively faint compared with the brilliant chromosphere that we are looking at. So I've had to up the gain, and here I am. I'm playing around with the conditions that I'm using to video, increasing the exposure, just to bring out a little bit more structure, more of the faint stuff in this arc prominence that we're looking at here. And then a little bit later on, I'll back off the exposure. There we go, just to show the fine structure in the prominences closer to the solar disk. And once again, I would estimate, gee, the length of this prominence, it's highly foreshortened because it's probably going around the edge of the sun, but it might be 20 or 30 diameters of the Earth long, or perhaps even longer, 50,000, 100,000 kilometers long.
Very, very big, hey?
Very big indeed. And if I play this video for, well, if I videoed this prominence for 10 or 15 minutes, like Lee, I would be storing up huge amounts of gigabytes of video. I don't have the prodigious amounts of terabytes that Lee has, but ladies and gentlemen, in that 10 or 15 minutes, you would actually see this prominence changing its shape, its structure, because this is a dynamic phenomenon on the sun. It will change before your very eyes. And how good is that?
It's pretty impressive,
Okay.
isn't it? Now I'm going to share.
You can even
quickly
see some changes. Yeah.
We'll go back to that. Go back to that.
I was just going to say you can even see some changes in the short period of time, I think. Like in the low, or maybe it's just because you're increasing the.
I am increasing the gain.
Yeah,
increasing the gain, yeah.
But as I said, these are dynamic. Over 10 or 15 minutes, you will actually see changes in the structure of these features. So our sun is dynamic. It is always changing its features, and that's why solar study is so wonderful. Our very own star, the closest star to us, a huge mass of incredibly hot plasma, and it's just wonderful to be able to look at it up close like this and to enjoy it. Oh, okay, I'll stop sharing that.
Well, it's back to us again. I think the videos are much better to look at.
Yeah.
Okay. No worries.
I've got those images of Anne Marie is there.
Yep.
Like there's a couple with prominences, but I was just noticing even in this one, when you look here, even without the prominences themselves, you see all of this sort of a very rough and jagged sort of edge, which isn't going to be a focus type issue. It's
correct.
It's fairly obvious. That's all like individual
fires,
and it's just that.
Well,
like
there are little prominences, tiny things called spicules, and that is what is causing that sort of fuzziness. It's the fact that there are these structures coming off the disk of the sun, which and the entire disk is just covered. Sorry, the entire edge of the sun is covered by these tiny spicules that lead to that fuzziness that you are pointing out. Yep, it's wonderful to see.
Yeah. So the other couple of images were prominences.
There we go.
Yes, there we go. Beautiful.
So would this one here, do you think that would be sort of looping to down here, do you think? Or is that...
Well, yes. And particularly the one on the left you've got there, which clearly is a loop going over the edge.
Yeah, you can see it, can't you? It loops back over itself. No, the other way, Lee. Loops back that way. Yeah, and then straight back down again. You can just see it.
Yep.
Oh, yes. So it's sort of going...
Yeah, and then back down.
That way. Yeah.
That's it.
Yep.
So how tall can they get again, Russ? Those?
Well, they can get to hundreds of thousands of kilometers high. I didn't show it very long, but at the beginning of my presentation, there was a loop prominence, which was 500,000 kilometers long, I would reckon. On that 500,000.
Wow.
These are ridiculous numbers that really are a little bit beyond our comprehension. But yes.
So further than the distance between here and the moon. That's unbelievable.
Yeah. Almost double the distance between the Earth and the moon. Yes. And the amount of stuff, billions of tons of stuff held aloft by magnetic lines of force.
Sun's not playing ball today, but given it takes light around 8.5 minutes to reach us, can we ever really show it live?
No, we can't, and that's a good point you've made there. Yep. In fact, nothing is actually live, because even when you're talking to someone, it takes a few nanoseconds for the light to travel to you from that person. So nothing is truly nothing is truly live. This is true. Yes. But that is the beauty of astronomy, ladies and gentlemen, and girls and boys, that everything we look at up in the sky has taken a certain amount of time for the light to get to us. A little bit beyond a second for moonlight, which is reflected sunlight, 8 minutes and 20 seconds for sunlight to get to us, 4.3 light years for the nearest star, Alpha Centauri, in the nighttime sky, etc., etc. it is just a wonderful sense of going back in time with all these things.
Yeah, we have another
Okay,
question.
well,
We have another question for you, Russ. They're coming through.
wonderful.
Trent wants to know, and it's not a silly question, Trent, but do all stars have prominences, or is it just specific to our sun? So with
That's
all
a
the different
very,
types of
That's a
stars that are
very
out there.
in-depth question there, Trent. Thank you very much for asking it. And yes, all stars will have prominences. Our star is a typical star, really. The features that we see on our star are typical of all stars, but it's all of a sense of scale. There are stars called red dwarfs, and really the nearest star to us is actually a red dwarf, Proxima Centauri, but we need a telescope to see it. But red dwarfs, even though they're cooler and smaller, they have prodigious flares on them. Flares so bright that they can actually increase the amount of light that the star gives off by 10 times, 20 times in just a few seconds. So these are called flare stars, and the flaring, the term flare is a very apt description because it is actually explosions on the star which lead to flares, which increase the sun's brilliance by many fold. So yep, all stars will have sunspots and prominences, etc., and it's a matter of degree. Our sun is a relatively quiet star in comparison to the theatrics that other stars can get up to. We're very fortunate about that, actually. So here's a vision of the sun, just where I've increased the contrast to make the features stand out a little bit more, and you can see the filaments here, a filament there, the active regions there, and active regions here and here, and all that wonderful chromospheric detail on the solar disk, the solar chromosphere.
We have another question for you, Russ.
Wonderful.
The Comet King, Michael Mediazzo, wants to know, when will we see another Carrington event?
Well, that's an excellent question, Michael.
We don't want to see one, do we?
We don't want to see one, that's right. We don't want to see one. Ladies and gentlemen, just for information, the Carrington event occurred in 1859. And I wasn't alive at that time, although some days I feel like I'm about that old. But anyway, it was a massive flare erupted on the sun, which blasted billions of tons of solar stuff earthwards. And as that billions of tons of solar stuff passed by the Earth, the magnetic fields that were tangled up in that billions of tons of solar stuff interacted with the Earth's magnetic field, and that allowed all that solar stuff to travel down those magnetic lines of force into the Earth's upper atmosphere. And you might think, well, the Earth's upper atmosphere is 100 kilometers, 200 kilometers, 300 kilometers up in outer space, but those effects were felt on the Earth's surface. Those magnetic fields can create currents, electrical currents in the Earth's surface, and these currents are measurable. You can stick a couple of probes in the Earth, and you can measure currents set up. But worse, electrical voltages were set up in the mankind's internet of the day, which was the telegraph system, sufficient to cause the wooden telegraph poles to catch fire, to cause the telegraph wires to short out, and causing the telegraph operators to get electrical shocks. And this was happening hundreds of kilometers up in outer space, but the effects were felt here on Earth. And so if a Carrington event occurred today, imagine what would happen to all those satellites up orbiting the Earth. They would be cooked and fried because of the voltages developed on them. Our electrical systems would be shorted out, so we would be without electrical power for months, maybe not necessarily forever, but it might seem an incredible length of time. So really, life that we have come to enjoy, and hopefully you're still enjoying life during COVID, but our way of life would be severely impacted. Our GPS would be knocked out instantaneously. We wouldn't be able to, we might have to go back to maps to find our way around rather than having to rely on GPS, etc. So, to get back to Michael's excellent question, the Carrington event was not expected, not anticipated, because we didn't have any satellites up in space constantly looking at the sun. But now the information that these solar probes are sending back to us will at least give us some warning as to whether a Carrington event has occurred on the sun, and may give us a few hours to safeguard our satellites and our electrical systems on Earth, to minimize as much as possible the extremely damaging consequences of a modern Carrington event here on the Earth's surface. So, to answer the question, we don't know when the next Carrington event will happen. It will happen, but at least we will have some warning that it's on its way. So I hope that answers your question, Michael, and a very good question indeed.
Oh, we have another question for you, Russ. Guido wants to know, can you block out the sun's disk like during an eclipse to get better contrast on the flares? So when you're live imaging, can you set a telescope so that you can't see the main part of the sun, but you only see the outer edge in order to get better views of the flares, or well, the prominences?
Well, that's a very, very good question, Guido, and thanks for asking it. And the answer is yes, that is possible. The telescope would have to be tracking the sun extremely well, so that the sun is always centered on the disk, which we would call an occulting disk. Occulting means just blocking out. But the hope is that as solar activity rises, because the sun's activity is slowly rising to reach a maximum around 2024 or 2025, the prominences that we see around the edge of the sun will be much brighter, so that we don't have to overexpose the sun's chromosphere to see those prominences. We can see the prominences. Well, imagine looking at the sun as we see it on this video, with some beautiful prominences coming visible around the edge. That's what we would hope to see on the sun in a few years' time. So to answer your question, yes, we can do it if the equipment is properly set up to do it, but we are hoping that in a few years' time we won't need to be able to do that, because the prominences will be brighter and much easier to image alongside the bright chromosphere.
How long before that happens? How long before that happens? Couple of years,
Sorry?
3 years, 4 years before that happens?
2024, 2025 is the forecast prediction for a solar maximum.
So we'll be coming out of lockdown just in time.
Just in time. Fantastic. Perfect.
Yeah, right.
Couldn't resist. Do you have any other videos you'd like to share, Russ?
I think we could stop the videos, but I do have, like Lee has shown, I do have a couple of
images
that I've created from the videos.
Let's have a look at those, shall we?
Which are nice. So I shall open that up, go to share screen. So hopefully you can see that.
Yep, now we can.
So I've done exactly what Lee has done. The beauty of taking videos is that you can put them into programs like Auto Stack It, and it will select the sharpest videos, of which there are many, stack them up, and you end up with a result which is very, very detailed, very sharp. And I've just taken the grayscale images and colorized them with yellow to make it appear as a natural solar color. So there are the wonderful active regions here, active region there, filaments here, all that wonderful chromospheric detail there. And so that's the sun. I shall go back to probably my favorite image. Oops.
Probably. I'll pop it up as soon as it arrives on my
Here
screen.
we go. And go to share.
Technology.
An image
Technology.
of
Here we
the
go.
active ring.
There we go. That was from the video you showed us before,
From the
wasn't it?
video, yes. Just as the flare started, there's a little bright spot just here, and you can see the absolutely astonishing amount of structure around these sunspots. And in fact, sunspots, they have a darker inner region called the umbra, and a less dark or a lighter region around them called the penumbra. And you can start to see that effect here, the umbra and the penumbra around here. And sunspots, look, maybe you actually get a sense of 3D perspective here, that the umbra actually looks like it's a little bit deeper into the sun than the surrounding regions. And that is actually a true perspective, that the umbra is actually a little bit lower down than the surrounding, for want of a better word, the surrounding surface of the sun. And there's a filament which is connecting these sunspot areas and structures around here. I could look at these pictures all day, honestly, and just enjoy the spectacle of them. Fantastic.
They do. They're amazing to look at. Do you have any others you'd like to share with us?
I think that's everything that I've got.
There we go.
Mark and Lee.
It is a pity that I'm just looking up to the skylight now. The clouds are just hanging about. They're not doing what they're meant to be doing, which is a little bit frustrating. But we work with what we've got, and
Exactly.
at the moment we've got clouds, so pre-recorded is what it was.
Yeah, and Mark, I can assure everyone watching in that those videos are a pretty reasonable representation of what we would have seen today in live viewing. So you've all had as close to a real-time viewing of the sun today through those videos captured just a few days ago.
Well, it's better than not seeing anything at all, and hopefully the viewers have enjoyed the stream and learnt a little bit more about the sun. After all, that's mostly what it's about, learning about the sun. So thank you, Russell, for your time this afternoon and for sharing your knowledge of the sun with us. Thank you, everybody, for coming along to the solar session stream. The next stream is in an hour, well, just under an hour. It's our very first instrument making live stream. We're going to have the ASV section director, Mark Justice, come along, and I think there's 4 or 5 people from instrument making joining him. They're all going to give very short sort of 10-minute presentations on something to do with astronomy that they have built themselves. One of those things I can tell you is a backyard observatory. We're also going to have a look at, so the thing that we've been raising money for, the All Abilities Astronomy Project. Mark Justice is the man who's in charge of putting together and, I guess, testing the Naismith telescope that we're going to be putting up at our dark sky site for people with mobility issues to be able to have a look through a nice, high-quality, large aperture telescope that they normally wouldn't be able to see through. So he's got some footage or some photos of that telescope, and he's going to have a bit of a presentation on that particular telescope that we're currently building for as part of our All Abilities Astronomy project. So we'll see you all back here at 4 o'clock. As I said at the start of the stream, there are still raffle tickets left. A whole chunk just went during that stream. I think about another 20 just sold, Russell. So we're getting closer and closer to selling out of those tickets. The draw's at around about 9 o'clock tonight. So once again, thank you everybody for joining us, and I'll see you in about.
Also, just a special thanks to Anne-Marie for sending those other images of hers through.
Yes, thank you, Anne-Marie, for sharing those images. She can continue to lay horizontal. She didn't want to get up and send any more through, so she was thankful. We'll see you. I'll see you back in about 50 minutes. So see you shortly.
See you later. Thanks everyone for joining in.